Okay, so last class, we learned about how we can achieve this segmentation and post-estimation using deep learning architecture. So the core is this kind of encoder-decoder network that is composed of convolutional layers and subsequent transpose convolutional layers. Okay. So transpose convolution operation, it has the opposite characteristic to the convolution operation. And yeah, this kind of operation it has. Anyways, it is differentiable. So, and this is why the transposed convolution is called as the transposed convolution. Because this convolutional matrix is transposed in transposed convolution operation. So that's why it is called transposed convolution. And anyways, we can use this encoder-decoder architecture to map this input RGB images to this kind of segmentation map whose width and height is same. And this is the example code for implementing this encoder-decoder architecture. And this is the sample code to train that encoder-decoder architecture towards the semantic segmentation. And even we learned about how we can train that encoder-decoder architecture for actually estimating the image patch. Okay. And naively using this MSE laws to train the network to predict the image patch, then the patches looks blurred. So we learned this kind of adversarial laws that can compensate, this blurred, to make the outputs less blurred, okay, by involving these adversarial laws. And this is that. And also we learned how we can train our network for post-estimation task. And actually post-estimation is also the regression task. Okay. So given RGB image, we want to estimate XY, even Z coordinate for some of the predefined joint positions. Okay. And for doing that, let's say, there are 14 joints and we have to estimate their XY coordinate, then that problem is framed as regression task that have to estimate this kind of 28 floating values. Okay, so by collecting such X and Y data, and we can train the the deep architecture that predict this number of floating values. Okay, so actually that's the way to achieve this post-estimation. But one paper is insisting that this direct mapping to this XY coordinate value. Okay, so this is the XY coordinate value itself. So mapping this RGB image to some arbitrary coordinate values sometimes doesn't work robustly. So some researchers are insisting that we have to actually estimate this type of 2D heat maps instead of estimating the coordinate values themselves. We can estimate this type of 2D heat maps. Okay, so here 2D heat maps are designed to have some of the widths and height by the number of joints. Okay, so these heat maps and also widths and height, they are also downsampled from the original image size. Okay, let's say this is the original width and height of the original image, but this heat map, their dimension is, for example, downsampled by maybe 8. So we normally downsample it by number of 8. Okay. Anyways, and also we have to define the joint number of heat maps. So for each heat map, 2D heat map, some positions are activated, but we have a number of joint heat maps. So each heat map include where each joint located in. So we have to have J number of heat maps if there are J number of joint. Okay. And so some researchers are proposing that if we use this type of 2D heat maps instead of this low XY coordinate value, then the network can work more robustly than before. Okay. So this is the input image, and there are some differentiable layers, mainly based on the convolutional layer. And here you can see there are H prime by W prime by P plus 1 number of heat maps, okay? And that's actually this kind of thing. So from the input image, we have some differentiable layer and estimate the first heat map, and then also have some differentiable layers and map it to another heat maps. And also via some differentiable layer, we calculate another heat maps. So actually they estimate 3 times for the heat maps and also apply the L2 loss for each output. So by doing that, the paper authors are insisting that we can estimate pools more robustly than than estimating the low values. And actually, this is their code. Okay, so samely before, even though the problem is becoming complex, the core algorithm, the core implementation, their format is same as before. So we need to define our network here. So, this paper, their name is Convolutional Pose Machine, published in CVPR 16. So you can search for this if you are curious about this paper. Anyways, that's why here we are naming the architecture as CPN 2D pose. And this is our network's name. And here we have to, because this is the initial init method, we have to define our architectures here. So we have to define multiple convolutional layers here. And this is the forward function, okay? And you can see here we apply a lot of convolutional layers and also the nonlinear layer and max pooling operation. And then you can see in the middle, you can get the feature. We record that as the encoding variable. So this is our feature. And then we will apply for the convolutional layers and estimate one heat map. This score map is the heat map. And so we apply again, concatenating this intermediate score map with the feature vector. This is concatenation, and apply another stream of convolution and nonlinear layer and estimate the second heat map. And then again, concatenate the intermediate feature and the score map, heat maps in the middle, and apply another stream of convolution and nonlinear layer and estimate the final output. Okay. So actually here we are estimating heat maps 3 times, and we will apply the L2 loss on this output to train the entire network. And actually we will at the lab use the last heat maps as our final output. Anyways, this is even though this has bigger scale architectures, their core implementation is same as before, right? So we have 2 methods, the initialization method and the forward method. And in each, we have to implement our network and also how we can feed forward the network to get the final output. So this is the implementation of the pose estimation algorithm. Okay, so, and today we will also learn about how we can achieve the object detection task. Okay. So as I told you, object detection algorithm is doing this kind of thing. So we are assuming that the one image is composed of multiple objects when we conduct the object detection. And because of that, we had to specify the object's locations using the bounding box representation. This is the bounding box. And we have to specify where is the car and where is the human, okay? And then we have to classify each bounding boxes according to their semantic label, okay? And also we have to provide some of the probability for that semantic object, okay? So here again, this image is composed of multiple persons. So we have to detect where the humans are using the bounding box representation, and also have to classify each images contained in the bounding boxes according to their semantic label, and also provide some probability. Okay? That's the object detection task. And this is the semantic segmentation, and I already showed that we can achieve this using the encoder-decoder network. Okay? But somehow this object detection task is, sometimes more harder than the semantic segmentation, because here we can reuse the input dimension as the output dimension, and but in bounding box representation, depending on the number of objects, the final output dimension is not fixed. So sometimes, this object detection could be harder than the semantic segmentation to implement. Okay. So from now on, we will learn about how to implement object detection algorithm using the deep architecture. So, this is the naive implementation of the object detection algorithm. So, similar to semantic segmentation, this is the given image, and we can apply multiple scaled windows to the object, to the images, and we can make a lot of bounding box cropped images by sliding the windows in this manner, okay? From left to right and from top to bottom, we can apply bounding boxes in this manner to obtain these cropped images from the whole image, okay? And then we can apply image classification method that can classify whole images into semantic class, okay? So this, for example, if this is the cropped image, we can classify this cropped image into some semantic labels, okay? And by doing that, for all the cropped bounding boxes, okay, by classifying all the cropped bounding boxes into their semantic classes, we can detect multiple objects inside the whole image, okay? However, this kind of method is becoming very slow, because similar to semantic segmentation algorithm, let's assume that the width and height of the images are like this, 640 by 480. There would be this number of bounding boxes. And also, even more worse is, in object detection task, some objects are shaped as the square, but some objects, for example, humans, will not be fitted to the square bounding box, but instead they will be fitted to this kind of rectangular shape. Okay, so we may require even more bounding boxes compared to the semantic segmentation algorithm. In the semantic segmentation, we apply this type of single-shaped windows, but instead these windows are this time very small. For example, 16 by 16 or 8 by 8, because it represents only the small scaled patch around the centered pixel. So in the semantic segmentation, to classify each pixel, we use this type of very small scaled patches and use that in the sliding window manner. We can crop the patches inside the whole image and classify each patch. And we achieve the semantic segmentation. But in the object detection task, we require relatively bigger bounding boxes that can contain whole object inside. I mean, because of this, object detection requires multi-scaled windows. So it means we need, we need this number of CNN operation to classify each patch, each cropped region, where this B represents the number of types of multi-scale windows. Okay, so given this window, we need this number of operation, and for this window, we also need this number of operation. For this window, we also need this number of operation, and so on. Okay, so we need a lot of operation to achieve the object detection task using this sliding window method. Okay, so it takes a few hours to achieve the object detection using the deep architecture for an image. Okay, so it is very inefficient and it might not be practical. Okay, so the computer vision researchers are becoming to search for the way to achieve object detection in a more efficient way. But indeed, I mean, in the year of 2001, this is before the deep learning era. So in the year of 2012, the AlexNet appears, which is the first successful deep architecture that shows the state-of-the-art accuracy in ImageNet challenge. Okay, before this year, most of the algorithm is based on the classical machine learning algorithms, such as the boosting or SVM or random forest and so on. They didn't use the deep architecture as the main classifier. At that time, indeed, one of the successful object detection pipeline used this kind of sliding window approach. Okay, so as I mentioned, from left to right and from top to bottom, they apply this type of bounding boxes, okay, in the sliding window manner and make a lot of cropped images. Okay, and then they classify these cropped regions into some semantic. They classify these cropped regions if they have semantic regions or not. They apply that kind of classifier. So one of the successful face detection algorithm called as Viola-Jones face detector, they use this kind of method. Okay, so this is their algorithm pipeline. So this is denoting their human engineered feature called as hard-like feature. They apply this kind of human-made windows to calculate some pixel difference. Okay, so that's the hard-like feature they defined. And first, they make a lot of regions within the sliding window, and then they apply this kind of hard-like feature for each region. and also apply some boosting algorithm, which is one of the shallow learning algorithm, to classify each features into phase or non-phase. Actually, that is the binary classification task. Okay, they achieve this kind of binary classification to detect the phases. Okay, but a very good thing was normally phases are contained in this kind of squared bounding box, so there was not much scale issue for this Viola-Jones phase detector. Anyways, they had to indeed slide the windows for whole images and apply some of the classifier multiple times. But good thing was also boosting algorithm is also one of the fast algorithm. So the entire pipeline works actually very fast, even though they apply windows over whole images. Their execution time is less than few seconds. So still practical, okay? But the problem is our algorithm is not boosting, but some of the deep architectures called as the CNN. So this kind of achieving this kind of object detection things using the CNN in this manner is not practical. So early researchers are, considering to use some of the, refined image regions. Okay, so image regions, as I told you, we can generate it by applying it in this manner. Okay, but researchers become to know that most of bounding boxes are not very useful because they are not containing the foreground object. Okay, so they try to find image regions that are likely to contain the foreground object. Okay, that's the algorithm. The early computer vision researchers are trying to use. Okay, and this kind of algorithm is called as the selective search algorithm. So they try to figure out the image regions that are likely to contain the foreground object. So this is the example for that image regions obtained from the selective search. So for example, this bounding box and this bounding box, they are good image regions that are containing the foreground object. Okay, and this is also containing. This is the examples for some of the small bounding boxes that have the foreground object, but not completely containing those foreground object. Okay. Anyways, they are not having bounding boxes in these regions, which is not containing the foreground object. So they try to make good good bounding boxes that are likely to contain the object. And how they obtain it is this way. So they apply some of the low-level techniques. Okay? So they first generate from the input image, they first generate some dense, small segmentation maps. Okay, from the whole image, they cluster each pixels according to their color, texture, and size, shape similarities. Using this kind of low-level cues, low-level features, they cluster image pixels into very small-scale segmentation cluster. Okay, and then they merge them together if their color, texture, size, shapes are having the similarity. Then they merge those small-scale segmentation clusters. And after many iterations, they can make this kind of bigger scaled segmentation map, which may contain the object inside. Okay, but this is not perfect. Okay, there could be some exception. So that's why subsequently the researchers are continuously trying to improve this approach. But anyways, it works. Anyways, it works because the from the images, in images, I mean objects may contain similar color, texture, size, and shape. Okay, so I mean this kind of assumption is valid for foreground object regions. So if they make the bigger scale segmentations from the over segmented regions using their similarity, then this kind of resultant segmentation map may contain the the foreground object. Okay. So I mean, how to get this kind of segmented region considering their low-level features is they use the k-means clustering algorithm. They regard each pixel as the for example, if they can cluster each pixel's color feature using the k-means clustering algorithm and can generate this kind of segmented map. Okay, and also using different parameters, they can also generate this kind of normal clustered map and also this kind of over segmented map. Okay, they all use a different scaled segmentation map to eventually generate this type of bounding boxes that surround each segmentation regions. Okay. So this is the way to generate this kind of initial object proposal bounding boxes. Okay, and this is how they combine the over-segmented regions to a bigger regions. Okay, and also in the OpenCV, this kind of selective search algorithm is already implemented. So you can learn this code. Okay, and this is the visualization part, and this is the image read part, and the core part is here. And you can apply the selective search algorithm on this kind of image, and you can see some of the bounding boxes are generated focusing on the foreground object of the image. So using, thanks to this selective search algorithm, in the year of 2013, this RCNN algorithm have appeared. So they call this algorithm as the RCNN because R is denoting the regional things. So this is called as regional CNN. And they are called as the RCNN because they first apply the bounding boxes generated from the selective search algorithm. They used 1,000 to 2,000 bounding boxes generated from the selective search algorithm, and then apply to whole image and apply the CNN algorithm. First, they crop the region and rescale the region and apply those cropped patches into the CNN algorithm. And in the middle of the CNN algorithm, you already know that they will generate some of the 2D or 1D, one-dimensional responses. And using these responses as the feature, they train another SVM classifier to map those features to the semantic classes. Okay. So are you guys following this? this is, are you guys understanding this, how RCNN works? Okay, maybe. So anyways, they apply the heuristic algorithm to generate refined bounding boxes, which may contain foreground object, okay? And then classify these bounding boxes using this CNN algorithm. So previously, I mentioned that there should be this number of, this B is the number of types of the bounding box. So this number of operations have to be there to classify all the bounding boxes generated from the whole image, okay? But here, we can just classify 2,000 patches, 2,000 regions only. So compared to this, which may take few hours to achieve the object detection for an image, we can greatly reduce the time complexity, okay? So we can achieve object detection within a few minutes, okay? So it becomes practical now, okay? We can greatly reduce the number of regions and thereby achieving the object detection using the deep architecture. But still, there are some of the limitations. Okay, still we are using many regions, which is not useful. So because of that, it is still slow. Okay, that's the first limitation. And the other important limitation is our algorithm start to train from this patch, this cropped patch, to the class label, okay? So actual training start from this cropped patch to map it to some of the class label, okay? I mean, this is the intuition for improving the RCN. So even humans require some context. So let's say we are cropping this region, let's say, and we can rescale to some of the fixed sized patch, and we apply some deep architectures to map it to class label. That's how this RCNN is working. But even humans, for example, let's say human is here like this. Even humans have to have information outside these patches to correctly classify this patch, whether it contains some object or not, okay? We humans are also, sometimes also require some information outside of this patch, okay? Here in RCNN, they only provide these kind of small cropped regions to classify it into some classes. So in that sense, this RCNN is limited, okay? They are not end-to-end trainable from this whole image. They only can start from these small patches already losing some contextual information. But when doing object detection, even humans are exploiting such contextual information inherent in the whole image. So, ideally, we have to exploit whole images instead of this small cropped region when training these deep architectures towards the object detection task. Okay. So the other problem is, they are not differentiable from the whole image, but they can only trainable from the small patches. Okay, that's another limitation in RCNN. So the next algorithm you have to know is this fast RCNN algorithm. Actually, this RCNN is the first object detection pipeline proposed, okay, to use the deep architecture, which is the CNN actually. they first proposed in 2013, right after the year the AlexNet comes. Okay, so actually here they use the AlexNet as the CNN architecture. But fast RCNN tried to improve such inefficiency, such limitations that I mentioned here. It still exploit a lot of bounding boxes, which might not be useful, and also it is not end-to-end trainable from the whole image. So they actually, some of the computer vision researchers, they try to propose this fast RCNN network. So their motivation is they try to apply the earlier layers of the CNN algorithm. I mean, CNN is, as I mentioned, composed of two parts, the convolutional layers, which process the 2D signals, and then they flatten the intermediate responses to 1D signal, and they apply the fully connected layers at the end. Okay, that's the normal CNN architecture, and eventually they map it to some probability vector that denote the probability for each semantic classes. So any layers to the whole image. Okay, in this algorithm, they propose to do this, and then the intermediate layers will be in the 2D space. Okay, we can obtain this kind of 2D feature map instead of the one-dimensional feature vector. We can get this 2D feature map, but very important thing is you already learned about the convolutional operation, right? So we apply for this image, we apply this kind of small filter kernel to generate this kind of output map. Okay, so input, this is the filter. Okay, so we apply that first to this region and generate one output pixel. Okay, and then slide the filter kernel to generate another output pixels. Okay, the important thing you have to note is some spatial informations are retained in these output responses. When we apply the filter kernel, I mean, for the convolutional operation, these regions are containing the information which is retained in this input region. And this output region retain the information comes from this input region. Okay, are you agree with this? Okay. I mean, when applying convolution operation, some spatial information is retained. Okay, so I mean the output, the intermediate responses after applying several convolutional layers, these feature maps are having the information for these regional input maps. And these output features are encoding the features for these input signals. Okay. Anyways, when we obtain 2D feature map by applying multiple convolutional operations on whole images, the same is valid. These regions are encoding the 2D features for original images, the left top part of the original input image, and this feature map is encoding information contained in the bottom right part of the original image. So it means some of the spatial information is retained in this 2D feature map. Okay, so what they wanting to do is they want to, instead of cropping the image itself, their motivation is they want to apply this selective search algorithms bounding boxes on this 2D feature map. Okay. By doing that, we can accelerate the inference of the overall pipeline. So previously, when we try to crop the overall images using the selective search bounding boxes, then we have to make this number of cropped regions, and also we have to apply, subsequently, we have to apply the same number of CNN operation to map it to class labels, okay? But here, what we want to achieve is, we just once apply the CNN, earlier layers of the CNN operation to generate the feature map, okay? This is very fast compared to the previous one, 2000 versus 1, okay? And then we will crop this feature region using bounding boxes from the selective search algorithm. And then this kind of cropped feature map, we will apply remaining fully connected layers to estimate new class probability. And here we also refine their bounding box coordinate. Okay, this is the regression task. We directly infer the new coordinate for this bounding box, slightly improve the initial bounding boxes. Okay, anyways, we apply two losses to train these two things. We have to estimate the class probability for each bounding box. At the same time, we will slightly refine the initial bounding box, applying this kind of two losses. Greatly reduce the inefficiency in RCNN algorithm. We can just extract one feature map by applying one-time convolution, okay? But subsequently, we may apply multiple fully connected layers. Here we have 2000 2D features again, but already we greatly reduced the inefficiency in the earlier stage. Okay, so the remaining part is same as previous one, but the earlier part is greatly becoming efficient. So the entire network becoming efficient. And another limitation is, the second problem is, reduced. The slow problem, they are improved by applying this convolutional operation for the whole image. And the other part is, previously we start the training by first cropping the regions, okay? The only trainable part starts from, they are limited for this part. But now we can indeed say this whole pipeline is end-to-end trainable, okay? So we actually start the training component from the whole image, okay? This part is trainable, and there's no non-trainable layers in the middle. So this loss from the whole image to this final loss, there is none trainable part. Okay, so this this entire network, we can call that as the end-to-end trainable architecture. So the first problem in RCNN is also they are solved. Okay, so now we can say when classifying this patch, we can say we are considering some of the contextual information from the whole image. Okay, so because extracting this feature, when extracting this feature, some of the contextual information is already considered in this when calculating the features for this region. Okay, so we can interpret that we we encode some of the contextual information from the whole image into this feature. I mean, this feature, okay, regional features, okay. So, fast RCNN, we obtain two characteristics. So it is faster than regional RCNN, okay, because it solves some inefficiency problem in earlier part, okay, and also it is robust, more robust. Their accuracy becomes more robust than RCNN because they are end-to-end trainable. Okay, they somehow considers the contextual information outside the regional information, so they are becoming more robust than RCNN. Okay, and this is the some of the loss functions defined. So here we use two types of loss. Okay, the first one is the this log loss is similar to this log loss is similar to cross entropy loss. Okay, so you can see that this is actually same as the cross entropy loss, and they are used to train the classification network. So to classify each region into a semantic label, we use this type of log loss. And also we use this type of smooth error loss to refine the initial bounding box location. Actually, they are same as mean square error loss we already learned, which is the L2 loss, okay? But they define the refined version of this MSE, and their function is looks like this. So, but it looks like this. When X is this region, this is smooth error X, okay? When X is -1, X lies in this region, their function looks like this, okay? But otherwise, they will be like this, okay? So, in this region, they are actually the L2 loss. This is actually the L2 loss. But when their discrepancy is larger, they experimentally validate that this type of L1 loss is efficient to close those, two ground truths and their predictions. So they use this kind of smoothed error loss. Okay. So this is another improved loss functions. Okay. So anyways, they use addition of this class loss and also the this error smoothed loss, which is the location loss, to train the overall network. Okay. So this is the overall loss, and this is the each component. Okay. And error smoothed loss is further explained here. Okay. So actually, this is the fast RCNN algorithm. Okay. Any questions till now? Maybe easy. Okay. Okay. And next, I will explain the faster RCNN algorithm. Okay. Here the algorithm is fast RCNN algorithm, but here is the algorithm called as the faster RCNN. Still here, they greatly improved the inefficiency of the RCNN algorithm, and also they improved the non-differentiability of the earlier layers of the RCNN network. But still, there are some bottlenecks in the region proposal algorithm of the fast RCNN. So as I mentioned, region proposal algorithm is, you can think that they are same as the selective search algorithm to generate 2000 bounding boxes. They are not very accurate sometimes because they are based on some rough assumption that the foreground object may have coherent color textures inside. So they cluster the overall images into using some low-level features such as the color texture. They cluster each pixels of the whole image into several clusters and define the sample, the bounding boxes based on that. So that's having a lot of heuristics inside. So this faster RCNN algorithm try to solve those kind of heuristics inherent in the fast RCNN algorithm. So this algorithm works similar to the fast RCNN algorithm. So they apply the convolutional early layers of the convolutional layers to the overall images, and then obtain this kind of two-dimensional feature maps. And previously, we crop those features instead of the overall images. In the feature level, we crop the features and apply FC layers after that to map it to the semantic classes. Okay. This overall pipeline is same as the original fast RCNN algorithm, but the difference lies in this part. Okay. Previously, we used the selective search algorithm, which is the heuristic algorithm based on the k-means clustering algorithm, to generate 2,000 object proposals. Okay, but here we involve this kind of RPN, region proposal networks, that actually is trained to generate this kind of proposal, bounding box proposals from the feature maps. Okay, so instead of involving this kind of clustering-based algorithm, we actually train the network that can estimate object proposals from the feature maps. Okay, so clustering algorithm, it is actually very slow because they inside their algorithm, for example, k-means clustering. I'm assuming that you are already knowing this k-means clustering. They involve a lot of iterations inside, okay? Because, and also they are having some of the heuristics, okay? They have a lot of iterations, so they are slow and non-optimal, okay? But when we train the network that can estimate this kind of object proposals, we can one time, by applying this feature map to the network, we can one time get the output, the object proposal, so it becomes fast. And also, because we are training that using the data, that is becoming optimal. Okay, so we can, by involving this region proposal network, we can actually solve the bottlenecks, the inefficiency, and non-optimality of the region proposals of the fast RCNN algorithm. Okay, so that's the summary for this fast RCNN algorithm. So this is a comparison between these three algorithms: this RCNN, this fast RCNN, and faster RCNN algorithm. Okay, so RCNN, we first extract the image regions using the selective search algorithm, and maybe we can obtain 2,000 regions. Okay, and we have to apply one CNN per each region, and that requires 2,000 CNN operations. Okay, still large, but becoming more practical compared to the sliding window approach. And we classify the features extracted from these CNNs, okay, into the semantic classes. Okay, and it takes in few minutes. Okay, the RCNN, it takes few minutes, and their accuracy is like this. On the this Pascal VOC 2007 data. And fast RCNN, we apply one CNN on the entire image, and extracted features are cropped based on the selective search bounding boxes. Okay, we anyways crop the feature level cropping. Okay, and classify each features into semantic classes. Okay, that's the fast RCNN, and I mean compared to the RCNN, it greatly reduced the time complexity. Okay, it takes few seconds now, and also you can see their accuracy is becoming better compared to the RCNN by removing some, non-differentiable part of the earlier layers. They can consider some of the contextual information contained in the overall images when classifying each page. Okay. And then fast RCNN, we also further remove the inefficiency and non-optimality in these object proposals. Okay, and then further make it efficient and further make it robust. Okay, so this is the important algorithm, early algorithms when to achieve the object detection task using the deep architecture. Okay, so but we have also, you may heard about the YOLO algorithm, which is also the famous object detection pipeline. Okay. Compared to the YOLO, we call these RCNN stream algorithms as the two-stage algorithm. Okay, because at the first stage, we try to extract the features for some of the cropped regions, okay, and then we classify those features. Okay, actually, this type of RCNN algorithm is composed of two stages. First stage, we get a region-wise feature. Second, we classify them. But YOLO, that is called as the one-stage algorithm. And we will maybe learn about this after the midterm. Okay. But anyways, this is nowadays becoming very critical because it is composed of one stage. It is very fast, even faster than fast RCNN. And also at the earlier YOLO, its accuracy was not very good. YOLO nowadays having version 12. Okay. YOLO version 1 through 3, their accuracy is less than these RCNN based ones. But nowadays, they are actually becoming very robust and fast. So nowadays, people are more and more use this YOLO. And this YOLO is very critical nowadays. But anyways, this is very important milestones to understand how the architectures are applied to the object detection task. Okay. And another important algorithm you have to understand is transformer architecture. Okay. Nowadays, transformer-based object detection pipeline that is actually replacing CNN-based ones. Okay. So their algorithm is called as DETR. Okay, so we will learn about that in the subsequent materials. So this is the DETR architecture. Okay, but before that, we have to learn about how this transformer works. Okay, and we have to explain that from the earlier NLP networks. Such as the RNN and LSTM. So we will learn about this in the next class. Okay. So for today, let's finish here and see you this Wednesday. Okay, thank you.